Here we have the bonus question from a final exam from December 2017. Question asks us to use the formula given in question 6c, which was this, that the integral from 0 to a of f of x dx is equal to the integral from 0 to a of f of a minus x dx, which we proved in a previous video, when f of x is continuous on the interval from 0 to a. We're going to use that to evaluate this other expression down here. So we're going to find the value of the integral of from 0 to pi over 2 of sine of x over sine of x plus cosine of x dx. So it looks a little bit complicated. If you think of our integral calculus toolbox, you might be thinking, well, maybe we could try integration by parts or u substitution or something like that. And as soon as you try that, you'll realize that this is a lot more complicated than it looks like it could be. For example, if you have sine of x as your u, well then your du, your derivative of that would just be cosine of x, but then your cosine of x is just sort of trapped down here in the denominator. And if you say that, oh well, maybe you could put a negative here and a negative here, and maybe cosine of x is your u, and then negative sine of x would be your du, well then you also have a du down here, which sort of complicates things. You have to negotiate for this sine of x down here. And as soon as you try it, and I would invite you to try it so you could see just how complicated it could be, you'll realize why it might be wiser to try to find an easier way to evaluate this, which is what I'm going to show you. So let's say that in the expression that we looked at, our integral from 0 to a of f of x dx equal to our integral from 0 to a of f of a minus x that we've already proved. If we let a equal to pi over 2, well then supposedly this expression here just becomes this. So everywhere where we have an x, we're just going to plug in our a minus x, or our pi over 2 minus x. So notice here we have a sign here, we have a sign here, here we have an x, here we're just plugging pi over 2 minus x, sign here, just plugging for x here, cosine here, just plugging for x here. And we're going to say that these, if this is equal to this, well then it must be equal to some sort of sum, and we'll just call that s that we're trying to evaluate for now. So this is equal to this, which is equal to s. Both are equal to s, we're claiming. So before we really get into this, let's just review a little bit about our sine and cosine functions and our trig identities and see what we can apply to this. So here in the green we have our sine function. Here in the blue, sort of the dotted line, we have our cosine function. And recall that because our sine function is odd, it's oddly symmetrical about the origin, well then sine of negative x equals negative sine of x. So for every x in the positive direction, there is an x in the negative direction that the output of the function is the opposite of. So just imagine our sine function just continues here off the paper. But cosine is an even function, meaning that it's evenly symmetrical about the origin. So cosine of negative x, well that just equals cosine of x. So for every cosine output in the positive direction, there is a cosine output in an equal negative direction that is equal to it. So hopefully that makes sense. One more last step here. I want you to note that when we plug when we plug pi over 2 minus x into our each part of the function here, we can use these identities to figure out what would happen if we just swap the x and the pi over 2 around. Just by definition, our x is going to be smaller than pi over 2. So when we swap these around, this is going to be a negative value now, and just like we had a negative x value up here, we can pull the negative out front here. So if we swap these two around, we just put a negative out front of everything. But sine of x minus pi over 2, just by trig identities, this equals cosine of x. And if you don't believe me, well, you don't want to just blindly take my word for it. Let's just look at an example here. Sine of, let's say if x equals 2 minus pi over 2, so that puts us over here. So the negative of this sine value right there is equal to the cosine value where we started. So sure enough, if we took the negative of this, this would put us down here, which would be in line with where this value is down here. And similarly, because cosine of negative x is just equal to cosine of x, we can just swap the pi over 2 and the x around freely, and we would have the same output. So cosine of pi over 2 minus x, well, this is just equal to cosine of x minus pi over 2. And just by trig identities, cosine of x minus pi over 2 is going to equal sine of x. And again, if you need just a quick refresher, or if you just don't want to blindly take my word for it, let's just see an example of that. Cosine of x, let's say x equal to 2 again. Cosine of 2 minus pi over 2, well, that's just going to put us over here. And when we take the cosine of that input, that puts our output right up here on the blue line. And we're saying that that equals to sine of when x is equal to 2. So sure enough, when x is equal to 2, our sine output is right there, and you can see that this is in line with that. So in other words, what we've shown is that when we just plugged pi over 2 minus x into our formula, we actually created an output that's just as simple as what we started with. So here's what we got when we just plugged pi over 2 minus x into our expression. And we have just shown that this equals this, because the sine of pi over 2 minus x is just equal to cosine of x, like we saw on the previous page. This is equal to cosine of x. Cosine of pi over 2 minus x is just equal to sine of x. So in other words, the expression that we started with, the integral from 0 to pi over 2 sine of x over sine of x plus cosine of x dx, is just equal to the integral of from 0 to pi over 2 of cosine of x over sine of x plus cosine of x. And again, we're claiming that that equals some sort of sum s. Well, what we can do is we can just take these two expressions, we can add them together, and because one equal thing added to another equal is just going to be 2 of that something. So we can go a step further and combine our integrals via our integral properties, and because both of these expressions are over the same denominator, well, we just add the numerators together into one numerator here, and that gives us sine of x plus cosine of x over our common denominator, which was sine of x plus cosine of x. Well, notice that this is the same thing, sine of x plus cosine of x over sine of x plus cosine of x. Anytime you have something in a fraction over that same something, well, it's just equal to 1. So that simplifies things a great deal. Here we have our integral from 0 to pi over 2 of 1, and when we integrate that, we see that the parent function of that is, or the big F, or however you want to think of it, is just x, evaluated from our lower bound 0 to our upper bound pi over 2. And when you evaluate this, you just have, when you just plug pi over 2 is x, or 0 is x, this just gives us pi over 2 minus 0, which of course is just pi over 2. And again, we're claiming that this, because we added these two expressions together, is equal to 2, twice the sum that we care about, 2s. So just doing a little bit of algebra here. As pi over 2 equals 2s, give us a little bit of a drum roll here. If we just divide both sides by 2, or multiply both sides by 1/2, we get that pi over 4 is equal to s. So we've just taken this rather complicated, deceptively tricky expression to evaluate, and using our trig identities, we've proven that it equals pi over 4.